Hello and welcome. Let us continue the discussion on optical amplifier and noises in the optical amplifier. Last time where we left, we were actually trying to determine the autocorrelation of the current I of t, the photocurrent, under the assumption that we have actually given some optical power to it. Of course, if there is no optical power, there will not be any photocurrent, and we ended up with an equation that looked like this. We had two terms, one term had nk square because k was equal to L, and the other term corresponding to all the non-overlapping intervals. Now, here is where we will use one of the Poisson distribution formulas. Okay. The distribution is Poisson and not a Gaussian distribution, because Poisson distribution is well suited for photon counting applications, and this is something that actually ties up to that one. The idea of a Poisson distribution is that in a given time interval, the probability that you actually receive n photons or generate n electrons, any n type n such things, is given by some e power minus lambda, lambda power n divided by n factorial, where lambda is the average value. Okay. It turns out that for Poisson distribution, both mean as well as variance both are equal to the average value lambda or the value lambda. Okay. So, going back to that, if we consider all these nks as random variables which are Poisson distributed, okay, so these are Poisson distributed random variables, then E of nk square, which is the variance of this particular random variable nk, is given by lambda of k delta t. Okay. So, lambda evaluated at k delta t is a non-uniform Poisson distribution, which means that it simply depends on time. Okay. And what about E of nk and nl? Well, these are actually the ones which are independent Poisson random variables. Therefore, their expectation would be slightly different. So, the expectation here would be that E of nk times E of nl. So, it would be independent variables, independent random variables. Therefore, they would be product of the individual variables. So, this is lambda of k delta t and this is lambda of L delta t. So, substituting these three into the equations that we have, right. So, you remember the two term equations that we have, and simplifying, what you get here is that E of I of t1, I of t2, given the fact that you have some optical power, is given by E square integral lambda of tau h of t1 minus tau h of t2 minus tau d tau, where tau goes from minus infinity to plus infinity, plus 2, because of this lambda of k delta t, lambda of L delta t, the result will be two integrals, which when you integrate is going to be E of I of t1, given that you have sent some power, times E of I of t2, given that you have sent some power. Okay. But we already know what these are. Remember, these are nothing but E times lambda and integral of that one. So, there is going to be 2 times E of that one. So, we can rewrite the second term as E eta by h nu whole square, one E eta by h nu coming from one expression, the other E eta by h nu is coming from the second one. Okay. And then you have two integrals, you have P of tau h of t1 minus tau d tau and P of tau prime h of t2 minus tau prime d tau prime. Now, let us consider an ideal impulse detector. In this ideal detector scenario, I have the pulse to be just an impulse function. Okay. So, the pulse shape that a current or an electron generates is given by the impulse function delta t, for which the integrals can now be simplified. The mean value of the photocurrent that you are going to get, provided that you have some optical input, is given by E integral lambda of tau h of t minus tau d tau. But I know that h is nothing but delta function. So, delta of t minus tau has this property that it would sift the value of lambda t out. It would simply pick the value of lambda t, because that is where it will be informally, that would be non-zero, right. So, this is actually E times lambda of t, that is it. Okay. But lambda of t is nothing but P of eta p by h nu. So, I can rewrite this as E eta by h nu P of t. Okay. Similarly, if I look at the autocorrelation, it would be I of t1, I of t2, conditioned upon the fact that we have received some optical power, and you can easily show that this is given by E square eta by h nu P of t1 and a delta function that depends on the time difference between T1 and T2, that is delta of T minus T1, plus you have the second terms which is E eta by h nu square P of T1 P of T2. Okay. Once you have this, now we can remove the conditioning on the fact that we have received an optical power. So, we can remove this preconditioning that we have done, okay. And when we remove the condition, you see the mean photocurrent I of t that you obtain is given by E eta by h nu, the mean optical power that you have received. Okay. We can rewrite this as E eta by h nu times P bar, where P bar of t is the mean optical power that is incident. Similarly, E of I of T1, I of T2, which gives you the autocorrelation, is given by E square eta by h nu and P bar of t, because the expectation goes on to that, and delta of tau, where tau is defined as T2 minus T1. So, tau is defined as T2 minus T1 is the lag that we are considering, okay, plus. So, you are considering 2 units, time T1 and T2, and you can see that this is a function of the lag tau. So, you can write this as P bar of t, which is the mean optical power, times delta t. The second term is E eta by h nu square P of t and P of t plus tau, because T2 is equal to t plus tau, and there is an expectation sitting onto this one. This expectation, let us call this as Lp of tau, where Lp of tau is the autocorrelation of the optical power, autocorrelation of optical power over here. Okay. Now, this is mean we have, autocorrelation we have, we can find what is called as the autocovariance of the photocurrent. So, autocovariance of the photocurrent I of t is obtained by subtracting this equation, okay, which let us call this as 1, and subtracting 2 from 1. Okay. So, if you subtract 2 from 1, what you get here is the autocovariance of the photocurrent, and that turns out to be the autocovariance of this one, which we can write it as Li of t comma t plus tau, okay, which is T1 and T2 terms. So, it is E square eta by h nu expectation of P of t delta of tau plus E eta by h nu whole square Lp of tau. Okay. So, this of course would be the function which is just a function of the lag tau. Okay. Now, here is where we need to go back to what is the power that has been incident. What power we have incident? Remember, the input signal power to the amplifier was S of t, which is given by square root 2p cos 2 pi fct plus theta, okay, where theta was the random variable, and then the power of course will be proportional to this. However, to this output of the amplifier will have, in addition to this one, it will also have the noise component n of t. So, this would actually be the total optical field that is coming out of the amplifier. So, you will have this as the signal field, and then you have the optical field over here. So, if you look at what is the power that is present, like this is the one that is going into the photodetector, correct? This has been the filtered. So, in the previous module n of t we had written it as nf of t, we have simply renamed that one as n of t, because that is the filtered noise is assumed over here. Okay. The power that you are going to get here can be evaluated by looking at the magnitude square of this term, and when you do that, you see that this is a square root of 2p whole square, and there is a cos square of 2 pi fct plus theta. So, when you break that down into 1 plus cos 2 theta, you are going to get a half, that half factor will cancel with 2, and what you get is the power p in this term, and here you get interestingly E of n of t magnitude square, where E is the expectation operator. It turns out that this is nothing but the autocorrelation function of the noise process evaluated at a lag of 0. So, this is Rn of 0, which would be the component or the average power that is coming because of the noise, that is filtered noise. Okay. This is what you are going to get. There are of course the other two components that is coming because of the signal noise and the noise beating. So, what would those terms be? To evaluate those terms, let us look at this Lp of tau, which comes from taking the expectation of the power, optical power that you have. So, P at time t1, P at time t2, where you remember that t2 minus t1 is equal to tau. Okay. When you write down this equation, the total optical power that is coming in from this side will be the optical power, right. So, that would be S of t plus n of t magnitude square evaluated at t1. So, it would be S of t plus n of t. You also have S of t plus n of t magnitude square evaluated at t2. So, this is the optical power P of t1, this is the optical power P of t2. When you do this product, and I will leave this as an exercise to you, you can, it is a little bit of a tedious thing, but I will put this as a assignment problem. So, you can solve for this one and see for yourself that this can be written as 2 Rn square of tau, where Rn of tau is the autocorrelation of the noise process, plus you are going to get a term which is actually fluctuating at twice the frequency Fc, okay, twice the signal frequency, plus you are going to get the beating term 4p Rn of tau cos 2 pi Fct, which would be the band pass process sitting at Fc. This is the one that is centered at Fc. Rn of tau is the autocorrelation of the noise process. Okay. Substituting this Lp of tau into the equation for the autocovariance of the photocurrent, you will see that this can be written as E square eta by h nu p plus Rn of 0. Remember, this was the one that actually came out from the short noise component, and this is p plus Rn of 0. Where is this short noise component located? This actually has a delta of tau function, right, because it was delta of t2 minus t1. Then the next term that you get is E eta by h nu whole square times Lp of tau, where we have looked at Lp of tau, which I have left it as an exercise to you to show that here. Okay. Because this term is varying at twice the frequency component to Fc, so twice the signal frequency component, this can be safely eliminated. Okay. Now that we have eliminated that, you can actually find out what would be the overall the power spectral densities. So, if you take the power spectral density of this process, you are going to get Si of f, where f is the frequency. So, it would be E square eta by h nu p plus Rn of 0. This term is independent of frequency. Remember, the Fourier transform is such a way that if you have delta of t as the time domain function, then its frequency domain or the Fourier transform is basically a constant, right. So, for all the frequencies it would be a constant. So, delta of tau Fourier transform is 1. So, this is the term. Plus there are two terms, one term is Rn square of tau and the other term is the signal and noise beating, right. The signal is p cos 2 pi Fct, the noise is Rn of tau. So, this fellow will be the signal noise beating or the signal spontaneous noise, and then you have the spontaneous noise term that is beating. Okay. And the spontaneous emission noise process is given by eta E by h nu whole square, which is coming from this one, times 2 Rn square of tau. Okay. And the signal and the spontaneous emission term is given by eta E by h nu whole square, and there is this 4 p Rn of tau cos 2 pi Fc tau. The Fourier transform of this one should be the Fourier transform of the noise Sn of f, but that will be shifted by plus or minus Fc, right. So, you are going to get two terms, one will be at Fc, one will be at minus Fc. So, if you assume now the ASC noise of the optical amplifier has a power spectral density that is given by NSP G minus 1 into h nu. Remember, this is for an amplifier having a gain G and a center frequency Fc which is equal to nu, having a spontaneous emission factor NSP. This is the power spectral density. This power spectral density will be two sided. What we mean here is that over the bandwidth B0, which is centered at Fc. So, this bandwidth here is B0, the power spectral density here is given by NSP G minus 1 h nu. Okay. There will of course be one more term at minus Fc. So, you are going to get over the same bandwidth B, this would still be the same value of NSP G minus 1 h nu. But when you shift them, this is the power spectral density of the noise, but when you shift them to plus Fc and minus Fc, right, by shift them up by those values, the one that is at minus Fc will be shifted to the center. So, if you now shift this one to Sn of f plus Fc, this term will be shifted down to the baseband level, this term will also be shifted to the baseband level, and one term will be thrown out into 2Fc and minus 2Fc. So, effectively what happens is that this spectral density gets pushed into the lower frequency, 0 frequency, at which point you are going to put a electrical low pass filter having a bandwidth BE. BE is considered to, B is taken to be less than the optical bandwidth B0, sorry, this bandwidth is B0, right. So, when you shift it down and then evaluate the total power by obtaining the area under the curve for this one, you are going to obtain the total signal to ASC noise beating term. I am not going to show this one, but you can, again I will put this as an exercise for you. You can see that once you have translated it down, then all that is required is to multiply this by a factor of 2 times BE. Okay. So, when you do that, the signal spontaneous variance you are going to get will be 4 eta E by h nu whole square. Please remember that this is nothing but responsivity r square g minus 1 P in, where P in is the input power, okay, NSP h nu times BE. The optical bandwidth will be sitting here, right. So, this would be the optical bandwidth and this area is not accounted for. So, this is at minus B0 by 2 and B0 by 2, but B is lower than B0 and therefore, this would be out. So, this is the signal spontaneous term. The spontaneous noise process is actually slightly interesting and slightly more tedious to evaluate. You see that this will have a Rn square of tau. If you look at the power spectral density, this turns out to be the convolution of Sn with itself, okay, and you actually have rectangular shapes for the power spectral density. When you convolve this with itself, what you are going to get is a triangular shape, okay. So, you are going to get a triangular shape, you can do this for yourself. The width gets extended from B0 by 2 to B0 to minus B0 and the amplitude here is N0 square B0, okay. And now you are looking again at the power that is contained within this bandwidth, which is minus BE2 plus BE. To find out this area under the curve, you have to do some integration, which I will leave, as I said, as an exercise to give you the spontaneous noise term, which is given by 2 eta E by h nu whole square N0 square B0 BE minus BE square by 2, okay. Please remember that we have derived this under the condition that BE is less than B0, okay. So, for this condition you see that this is given by this and N0 square is the noise power that is actually sitting inside the optical short noise itself, okay. So, this is the way in which, and N0 is basically given by NSP G minus 1 into h nu, okay. So, this is all that we wanted to talk about for the different noise terms. So, it is important to look at what has happened over the last 2 modules. Please remember that we have looked at the autocorrelation or the autocovariance of the noise of the photocurrent. Photocurrent has a certain amount of noise associated with that, and from there we were able to look at 2 terms. One is the signal to spontaneous noise variance, or that comes from this one, and then you had another term that is coming from the spontaneous emission term, okay, that is this fellow, and finally you had a signal term, okay. So, signal term was fairly simple and that came from the short noise component. So, when you actually look at what is the output of your amplifier noise, you will see that you will have signal term, you will have signal spontaneous as well as spontaneous noise beating, okay. So, the total noise variance that you are going to get from this one will depend upon the short noise component, okay. The short noise component was given by Rn of 0 plus P, okay, and then you have the signal spontaneous term and then spontaneous term, okay. Anything that I have missed over here, I would again refer you back to the paper that we talked about, R. Ramaswamy and P. A. Humblet. So, this paper in the appendix actually derives all these power spectral densities. Once we have these power spectral densities, we might be interested in finding out what is the effect of putting an optical amplifier on the signal to noise ratio, okay. To evaluate that one, let us look at this situation, okay. We have some optical input to this, okay, and then there is an amplifier with a gain G. This optical input might, if you give it to a photo detector, will produce a certain photocurrent, and therefore there will be a certain signal to noise ratio here. If you assume an ideal photo detector, then the ideal photo detector will not introduce any noise, but it will not introduce any this one, but it will introduce a little bit of a noise, but that noise can be characterized by looking at the input signal to noise ratio. If you now put in one more photodiode, okay, this photodiode would also produce a signal, okay, the photocurrent, which is now because of the amplifier it would be higher, but there will be a signal to noise ratio at the output. We define the noise figure as the ratio, signal to noise ratio input to the signal to noise ratio at the output. Let us quickly evaluate these two terms. Okay. If you just have a photodetector, of course followed by some load resistor that you have, and assume that the input signal is fairly large enough so that this is short noise limited. Okay. So, if it is short noise limited, the signal power is given by R, which is the responsivity, times whatever the power with which you have actually come in with, right. So, the input optical power is, let us say, Rp in. This is the photocurrent. Photocurrent square times RL will give you the signal power divided by noise spectral density, or the noise power is given by 2Q Rp in, which is the photocurrent, times Be is the electrical band pass filter. Okay, we are implicitly assuming that you have an ideal low pass filter after the photodetector having a bandwidth of Be, times RL, because this noise also gets dissipated in the load resistor itself. If you look at this, this would be the signal to noise ratio at the input which we are quantifying. Clearly RL will cancel with each other, and then one of the RPN will cancel with one of the RPN, and then you get signal to noise ratio as at the input as Rp in, which is the photocurrent, divided by 2Q Be. Is that okay? R itself is given by eta q by h nu times P in divided by 2Q Be. You can clearly see that this Q basically cancels with each of that, and then if you assume that this eta is equal to 1, you get P in by 2 Be h nu. Okay. So, you can assume that this is given by 2 Be h nu. Okay. Now, how about the signal to noise ratio at the output? Well, signal to noise ratio at the output is given by, so at the output is given by the signal power at the output. Now, the signal power has increased from P in, the signal power has gone up. So, the optical signal that you are going to get at the output of the amplifier is G times P in, G being the gain of the optical amplifier, times R times RL, right. So, this entire thing square times RL is the signal power at the output of the amplifier divided by the total noise that is contributed by the short noise as well as the amplifier noise. In the amplifier noise you have signal spontaneous and spontaneous spontaneous. If you neglect the spontaneous spontaneous noise as being too small, then the dominant component is only the signal power, correct. And of course, in addition to this there would be the short noise process. But the short noise process is fairly simple to see. This is given by 2Q GRP in, that is the signal power has increased now. BERL is the short noise component, and signal spontaneous noise component we have seen is given by 4R square GP in NSP G minus 1 H nu, this comes from the previous one, times BE times RL. So, this is your signal spontaneous noise term that has come in, and you can now cancel some of these factors and realize that this can be written as RGP in, RL cancels anyway on both sides, divided by 4R, let us call this NSP G minus 1 H nu as the power spectral density of the AC noise process. So, this would be 4R rho ASE within a bandwidth of BE plus 2Q BE. Okay. You can further simplify this equation, okay, by looking at what is signal to noise ratio at the input. It is given by Rp in divided by 2Q BE. Okay. So, you might actually rewrite this one. So, there is BE on common both sides. So, you can write this as RGP in divided by 2 R rho ASC plus Q BE can come out, and then multiply and divide by Q here. So, if you multiply and divide by Q, you are going to get Rp in divided by QBE. There is a 2 factor of course, because it is 2Q and 4R. So, 2 factor is there. So, these terms Rp in 2 QBE is nothing but signal to noise ratio at the input. So, now taking the ratio of signal to noise ratio at the input to the signal to noise ratio at the output, the noise factor or the noise figure can be simplified and written as Q plus 2R rho ASC, which is this term in the denominator, divided by Q times G. which can again be split into two terms. One is 1 plus G plus 2 R, and rho SE can be written as G minus 1 NSP H nu divided by Q G. R can further be rewritten as, you know, R by Q is nothing but eta by H nu, and then you can, you know, consider an ideal photodetector with eta is equal to 1, and then H nu here will cancel out with the H nu that is sitting in this numerator, and you get even more simplified expression of 1 plus G divided by NSP, which anyway cannot be removed, G minus 1 divided by G. If you assume G to be much larger than 1, which is what happens in practice, then the first term can be neglected, and in this term you have G minus 1, which can be approximately written as G, and then you have a G in the denominator, sorry, here there is a 2 in the numerator. So this would again be equal to 1, and then what you get is 2 NSP. So this noise factor turns out to be 2 times NSP, and NSP is the filling factor which we have defined in the previous one, given by N2 by N2 minus N1. Okay. In an ideal scenario, N1 is equal to 0, okay, so that NSP is equal to 1. Okay. And what you see here in the noise figure is that this would be then equal to 2 times, right, NSP is equal to 1, so it is 2 into 1, which is equal to 2. So the signal to noise ratio at the output of an optical amplifier followed by a photodetector is actually only half the times of the signal to noise ratio at the input. Okay. So you can see here that just because we are putting an amplifier, it does not mean that only signal is getting amplified. It actually has an effect of having both signal as well as noise, which worsens the signal to noise ratio. Okay. And this worsening is by a factor of half in the best possible scenarios, and half if you take the dB scale turns out to be 3 dB. So even in an ideal kind of a situation, your noise figure is still worse by a factor of 3 dB. In practice, you get a noise figure anywhere from 5 to 6 dB. Okay. And this completes our discussion of the noise figure of the amplifier. In the next module, we will be putting up all the terms that we have looked at, all the components that we have looked at, and analyze what happens to the receiver side. Okay. We analyze the performance of the systems with, without amplifier, what would be the limitations of putting many amplifiers in the link, how should they be placed, okay, and then we will look at the statistics of the receiver signal. Thank you very much.